This is pre-calculus notes on section 7.3. Tangent, graph of tangent. All right, so definition: vertical asymptote, a vertical line that the graph of a function approaches but never touches or crosses because the function is not defined there. Make sure you have that in your notes. Moving on. All right, so here's your textbook view of the tangent function, okay? Let me just point out a couple of things. Let's take a look. Here, what I'm highlighting are vertical asymptotes. Okay, there's a vertical asymptote for tangent at every odd multiple of pi over 2. All right, and we've got a continuous function. Oops. Okay, in between those two vertical asymptotes. All right, so in just a second, we're going to create this from scratch. So blank screen. Okay. Let me go back again a second. The period of tangent is pi. Okay. The period of cosine and sine, of course, were 2 pi. But the reason that this has a shorter period, let me think about an angle in standard position, okay? Tangent is positive in quadrants 1. All students, it's negative in quadrant 2, positive in quadrant 3, and negative in quadrant 4. So what happens is, as we're going from quadrant 1 to quadrant 2, we've got one set of values, and then that repeats itself in quadrants 3 and in quadrants 4. Okay? And so that's why the period is only pi. All right, moving on. So what I'm going to do is I am going to graph this from negative, what did they do here? I'm going to graph this from negative 4 pi to positive 4 pi, which is what I did with sine and cosine, okay? And by now, you've set your axes up several times, and I'm not going to take any long time here to explain how I'm doing this. Okay. All right, as we said in the graph of tangent, there are vertical asymptotes at odd multiples of pi over 2, okay? Why is that true? Well, that's because the tangent function is undefined at odd multiples of pi over 2. So, let's see, I've got a vertical asymptote here, 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 here. Those are supposed to be straight vertical lines. Okay, and this is going to be a curve. If I'm going to start at the origin, the curve is going to be concave up to the right of the origin, concave down to the left of the origin, and it's going to be approaching those vertical asymptotes, okay? And here we've got zeros at every multiple of pi, okay? And then that same pattern happens. Concave up, concave down, concave up, concave down, concave up, concave down. Here I'm only going down, okay? Up, down, up, down, up, down, up. Okay, so I wanted you to see my rough hand. It's really tough to draw on this tablet screen. Hopefully yours are a little bit nicer. This is the perfect version, okay? That's what it looks like, perfect. This is my ugly version on the tablet. Hopefully yours is somewhere in between. All right, one cycle of tangent. Remember again that the period of tangent is pi. Now, because of the fact that if I were to go from 0 to pi, let me just draw what 0 to pi looks like. If I extend this out a little bit further and make this pi. Remember that tangent is 0. Oops. Tangent is 0 at all of the multiples of pi, and that there are vertical asymptotes at the odd multiples of pi over 2. Okay? So if I were to graph this between 0 and pi, which is the period, I've got a broken function. It's not showing the continuity. And so therefore, the one cycle of tangent is defined between negative pi over 2, that was cut off when I cut the picture, and pi over 2. Okay, we don't define a cycle starting at 0 when we're talking about tangent. Okay, so the domain and range. All right, so there are all of those vertical asymptotes are places that the graph does not exist, the function does not exist. Okay, so the domain is going to be all real numbers where x is not an odd multiple of pi over 2. All right, so where x is not equal to odd multiples of pi over 2. All right, so odd multiples, the algebraic way, let me just write it in English first of all. Okay, where x is not an odd multiple of pi over 2. Okay, the way that we write that in algebra is we say where x is not 2k plus 1 times pi over 2 for all k's that are integers. All right, that's the way you do it in algebra. The range is going from continuously, let me get the highlighter out, continuously from negative infinity all the way to positive infinity. There are no breaks in the range. So the range is all real numbers. Okay. Graph the function between pi and 2 pi. I'm going to do this very quickly. They're only asking for positive numbers, so I'm putting my y-axis on the left. The biggest thing they're asking for is 2 pi. Okay, remember that there are vertical asymptotes at odd multiples of pi over 2. Now, the only odd multiple of pi over 2 between pi and 2 pi is here at 3 pi over 2. There are zeros at all of the multiples of pi, and to the right it goes up, and to the left it goes down. All right, state all of the values of t for which tangent equals 1. All right, so it's a positive 1. Let me just draw someplace on the graph where it might be, okay? All right, so there's only one place per cycle. You know what? Never mind. I'm going to draw this graph near 0, okay? I'm just going to draw from negative 2 pi to positive 2 pi. So that we can see the so that we can see the repetition, the repeating nature. All right, so we've got vertical asymptotes at all the odd multiples of pi over 2. We've got zeros at every multiple of pi. Okay, concave up to the right, concave down to the left. Oh my, it's really sloppy. Okay, and now let me just mark where y equals 1 might be, okay? It happens once every cycle, okay? I'm going to use my trig card to determine the first angle. And I didn't prepare my trig card so that I could show it to you on the screen. But I'm looking at my trig card right now, and I see that the first time that tangent is equal to 1 is at pi over 4. Okay, so my use of 1 is pi over 4. Okay, and then it happens every pi. So if I'm writing an arithmetic sequence, the common difference is pi. All right, so here's my answer. I've got pi over 4 plus or minus pi. All right, that is all of the values for which tangent equals 1. All right, that's it.